Hello friends, welcome to second session on the Ansys Fluent Learn from home. In our last session, we had seen the basics of the design modular. In today's session, we are actually going to model and simulate 2D fluid flow problems. Basically, we are going to take two problems and try to cover the entire simulation, how to create the animation, how to plot the graph and everything in this lecture. So hope you will enjoy the today's session. So without wasting our time, we will start with our today's session. So dear students, in our last session, we had covered the basics of all the design modeler. What are the different commands which are used in design modeler? In today's session, basically we are going to start with the problems. Today, our theme of this session will be how to solve the two-dimensional fluid flow problems. We are going to see the entire analysis of 2D fluid flow problems. So let's start our session. So first of all, we will click on the Ansys Fluid Flow Fluent. We are going to right click on the geometry because first of all we will like to model our problem, and we will click on the new design modeler. Okay, so we had entered into the design modeler. Then first of all we will change our unit to centimeter. Okay, because it will be convenient for us to work in centimeter. Then we will select the XY plane. We want to create a sketch on XY plane, so we will click the new sketch. So new sketch will appear. Okay, now I want to have my viewing plane perpendicular to this view, so I will click at look at. After that I'll go to sketching. In sketching I'll start sketching my model. Okay, so I'll consider a rectangle. Okay, I'm starting my rectangle from here. Okay, so this is my rectangle. I'll quickly specify the dimensions. So this will be vertical length. I'm going to define it as 20 centimeter. This is my horizontal length of rectangle. I'm going to define it as 50 centimeter. After that, I want to create a surface, okay, from this sketch. So I'll go to concept. In concept, we will select surface from sketches. Basically, we are working on in 2D analysis problem. So for that, we are supposed to create a surface. I'll select this surface. After selecting the surface, on where I want to create the surface. So I want to create the surface on sketch 1. So I'll apply sketch 1. Okay. Again, it will ask whether you want to add a material or add frozen. Okay. So I'm selecting add material. Okay. Then I'll generate it. So you can see my surface is created. Okay. You can see in two-dimensional view it is a surface. Okay. Which is created on XY plane. Now again now this is I'll consider this as the fluid flow path. Okay, now our problem which we are going to deal, it will be the formation of boundary layer over the flat plate. So we are supposed to create the flat plate. So again I am going to select this XY plane. We'll say sketch. So this is sketch number 2. We'll go to sketching. In sketching again I'll select one rectangle. Okay, so I am drawing one rectangle over here. Okay, now and after that I'll press sketch escape. Then we will go to dimension. Again I'll select the horizontal general dimension. I'll define this width as 45 centimeter. Okay, 45 is too close, so let's say it be 42 centimeter. So there is a gap of 8 centimeter. Okay, after that the vertical length, again general, vertical height of this rectangle, we'll select vertical this line and this line. Okay, so I want it for 1 centimeter, or let's say 2 centimeter. Okay, so 2 centimeter is the height of the rectangle. Now again we will go to concept, surface from sketches. Okay, we will apply sketch 2. Now here we are going to select add frozen. Okay, because if you are again selecting the add material, so basically these two surface they will combine and again one rectangle is formed. So basically they will unite with each other, but I want these plates different and fluid flow path different. So basically here I am going to use add frozen. Okay, after that I am going to select the generate. Okay, so you can see here this is our surface body 1. We can rename it as fluid. Okay, and this is our surface 2. We're going to rename it as plate. Okay, now if we hide the plate, so you can see there is some part of fluid which is passing through the plate surface. Okay, so basically we are supposed to separate them. Okay, so for separating them again we are going to make the use of boolean. Now how to use the boolean we had already seen in our last session. Again we will revise that. Basically you want to subtract. You want to subtract what? Is this hidden? Show what? Okay. So what will target body? Our target body will be fluid. What we want to subtract? We want to subtract the plate. And do we want to preserve the plate? Yes. Okay. So after that we will generate. So basically now the fluid path is this much and plate is this much. Okay. Now suppose I am hiding this plate. Okay, so now you can see the fluid path is this much. Okay, plate path from the fluid has been subtracted. So I'll say show all the bodies. Okay, so we had completed our modeling. Okay, whatever the problem which we want to model, we had done the modeling part. So we will go to file and close design modeler. Okay, after that the next component in C, I forgot to explain all this 5 component. So our first step in any CFD problem is to model the problem. So modeling has been done. Then the second step is meshing. Now what is the importance of meshing we are going to see. Okay, after that we are supposed to set up the problem, apply the boundary condition and do the calculation, and after that the results can be seen in CFD post. Okay, so one by one we are going to see them in detail. So modeling part, I think we had taken an entire session on modeling, so I think modeling doubts are clear to you. Now we will see meshing. So we will go to edit meshing. It will take some time to open the window, so we will wait. Okay, so the meshing window appears now. We had to wait till our model get uploaded. Okay, so our model is being uploaded now. Okay, so you can see whatever you had modeled in design modeler, it has been uploaded here or recorded here. Okay, after that we will see first of all how the meshing is done. Now see, meshing is, what is meshing? First of all, meshing is nothing but this entire model, it is divided into tiny parts, okay, or number of elements, and basically the calculations this Ansys software do for these elements based on the boundary condition applied. Okay, so meshing is very important. Okay, because in unstructured meshing basically you are not going to get the accurate results. Okay, so for accurate results you are supposed to refine the meshing, and the refined mesh is called a structured mesh. So first of all we will see the unstructured mesh. So we'll directly generate the mesh. Okay, so you can see this is a unstructured mesh. Okay, now basically we are going to structure this mesh. So there are different methods. Okay, meshing is a very vast field. Actually, there are separate software such as hypermesh, which is basically used for specific meshing purpose only. Okay, now meshing is a very big and vast part. We are not going to cover that much part. Okay, because actually this lecture will become short to explain all the meshing concept. So basically, just we are going to see for this model how we can refine the mesh. Okay, so we will go to sizing. Okay, in sizing I am going to select this. Okay, first of all, see from here there is a uh, uh, option of selecting a vertex or a point, selecting a edge, selecting a face, and selecting a body. So basically I want to size the edge, so I'll go to edge. Okay, after that I'll select this edge. Okay, then uh, apply. So one edge is selected. Now here there are different options. I can define the element size, or I can define the number of divisions. So I'm going to divide, I think the length was 50 centimeter. So I'm going to define this as 50. So there will be uh, 50 divisions. Okay, so you can say these are the 50 divisions, or let's say uh, 80 divisions. Okay, or keep it to 50, it will become simple. Okay, then I think this length was 8 centimeter. So again I'm going to mesh sizing. I'm going to select this edge, apply, and let's say its size is, or the division is 8. Okay, after that again we will go to sizing. We are going to select edge 1, edge 2, apply, then number of divisions, I think 8, so 42. Okay, after that again we will go to insert, sizing, edge 1, then edge 2, apply. I think height was 20 centimeters, so let's say 20. Okay, after that we are only left with this edge. So again we will go to mesh, insert, sizing, this division as well as this edge and this edge, apply. We will restrict it to 2 only, because we are making 1 centimeter edges. After that we are supposed to map all these edges, so we'll go to face mapping. Okay, where I want to map on this fluid surface, because the fluid surface is very important for our analysis. Okay, after that we will generate the mesh. Okay, so you can see now how this mesh has been refined. Okay, if you want you can further refine it. We can make it 200. Okay, here we can make it to 16. Okay, more refine is the mesh, more will be our accuracy. So 42 to 84. Okay, and I think 22 we will make it to 40, and this is 2 to 4. We had double them. Okay, and after that update the mesh or generate the mesh. Okay, so you can see more refined is the mesh. Now here you can see non-refined mesh, but basically here fluid flow is not going to take place. We will not bother about this meshing. Basically this mesh is almost structured now. Okay, after that the next step is define the boundary conditions. Okay, so for defining the boundary conditions we will again select the edges. Okay, now let this edge, we will create name selection and we will define this as inlet. Okay, so from here air will enter. Now we will define this edge. Okay, create name selection. We will define this as outlet. Okay, after that this edge and this edge. Basically this will be the boundary walls. Okay, so we are going to define this as walls or wall boundary for simplicity. Okay, and this edge 1, 2, 3 and 4. Okay, this will be the plate surface. So we will say wall plate surface. So in this way we can define the boundary condition to our problem. Okay, now whatever the conditions you had applied, you can check from here. This is our inlet, this is our outlet, this is our wall boundary, and these are the walls of plate surface. Okay, so we had set up the problem in our meshing. Okay, and here we had seen how to create the structure mesh. So we will close our mesh. After that we need to update the mesh. Okay, so you can again right click here and update the mesh. So you have to wait till a green symbol of tick appears on the mesh. Okay, it means the mesh is ready and we can apply the boundary condition in setup. Okay, so we had to wait till the green right tick appears in front of mesh. Okay, now we will go to setup and solution. So we will right click here and we will edit. Then we are always going to do the calculation with double precision. So we will click on double precision and we will say OK. After that we had to wait for a minute so that this Fluent modular will open. Okay, so now you can see our Fluent modular is open and our problem which we had set, it is being uploaded. The mesh is being recalled here. Okay, so we had to wait for a while. Okay, so now you can see our mesh is appearing here. Okay, so now our problem is set for post processing. Okay, so we will go to see the first here you can see the number of tools. So the first tool is general tool. Okay, so in general tool basically there are two types of analysis, study and transient. So basically transient analysis is used when we are going to consider the moving mesh. Here there is no moving mesh, so basically we can go with study. Okay, then already we are having a 2D space. So here we had 2D planar space. Okay, after that we will go to model. Okay, suppose in some case you want to apply the gravity, so you can apply for gravity and specify the value of gravity in x or y direction, and if it is downward, so it will become minus 9.81. But in our case gravity is not playing the role, so we will not apply for gravity. Then we will go to model. Okay, so in model, now see I am using Ansys Fluent 19. So my appearance will be a little bit different if you are using Ansys 20 or Ansys 16, but all these tools are same. Okay, only the appearance is different. As per the new versions are coming, they are modifying the uh, appearance only. Okay, now we will go to model. In model we will basically if you want to have a heat transfer between the flowing fluid, so you are supposed to apply the energy equation, but in our case there will be no heat transfer, so we are not going to apply the energy equation. Okay, after that which type of fluid model we are going to use. Okay, so there is a laminar model. If you want to go for a non-Newtonian fluid, Newtonian fluid, so you can select ideal fluid in viscid fluid. Basically the most prominent model is turbulent model, so we are going to use K epsilon model. Okay, here again various types of model are there, but we are going to use the basic model. Okay, so we will apply OK. After that, if radiation is taking place, so you can apply the radiation heat exchanger. Number of models are there, but basically in our problem we are not going to deal with them. Okay, so after modeling we are supposed to define the material. Okay, so we will go to material. See, in the material already the fluid material is air and solid material is aluminum, so no issue, we can have an aluminum plate. But if you want to add or subtract the material, okay, so in that case go to create. Okay, once you go to create, so basically material library will open. In the material library you can go to fluid database. Okay, so in fluid database these are the number of standard fluid. Okay, if you want water you can add water, water vapor you can select from here and copy. Okay, uh, also in solid number of standard metals. Okay, or some non-metals. Okay, they are already being added. And if you want to add a new material, so in our later videos we will going to see how to add the new materials. Okay, so already air and aluminum are there, so we haven't selected any new material. Okay, after that we are supposed to define the cell zone condition. Now we are having two types of bodies. One will be fluid, which we had defined, fluid domain, and second is fluid domain. So fluid domain, what we want it as a fluid. So already fluid is there. Okay, then we'll go to edit, and in edit which fluid, basically in our case only air, because we had defined the air only. Suppose we had selected the water, so it might have shown air and water. Okay, so okay, for plate it is already showing the solid and only one solid is selected, aluminum, so it will automatically take the aluminum. Okay, so for a plate the material is aluminum, so we'll say okay. Then the next is boundary condition. Okay, now you remembered in our meshing we had defined the names to different boundary conditions such as inlet, outlet, wall, so all that name will appear here. Okay, now we are supposed to define this condition. So first is inlet condition. Okay, we'll go to inlet. Which type of inlet? There are number types of inlet such as mass inlet, okay, pressure inlet, and so on. So we will select the velocity inlet, okay, which is a default. After that, click on the edit. Here we are supposed to specify the value, okay, at what velocity the air is coming. So we will say let it is coming at 0.5 meter per second. Okay, then outlet condition. Which type of outlet condition? Let it be pressure based. Whatever the value of pressure is there at outlet, we are okay with that. Okay, so we had selected pressure outlet. Then wall boundaries. Okay, so already the wall, all these walls, they are having default, by default wall, we had specified the wall, okay, with the boundaries, so it will directly take the wall. Okay, after that so almost our model is set. Okay, now we are supposed to run the calculation. So we will go in solution. In solution we will initialize the problem. So there are two types of initialization. I always prefer for standard initialization. Okay, from where you want to initialize? I want to initialize from inlet. Okay, so I'll select initialize the problem. So my problem is being initialized. Okay, after that I want to create the animation whenever the flow is taking place, how the boundary layer is formed, what are the pressure changes that are taking place, what are the velocity variation that is taking place. So I want that. So for that, once you initialize the solution, go in calculation activities and select this solution animation. Okay, once you select this solution animation, you are supposed to go in new object and select the contour. Okay, now here you are supposed to select where you want to create the animation. So I want to create the animation for interior fluid and plate. Okay, and for what I want to build for pressure. Here are the various properties. You can select the properties. Pressure, what type of pressure? Pressure, there are number of types: static pressure, pressure coefficient. So I want static pressure. Okay, I'll select save and display. Okay, so right now when no fluid is taking place, so you can see the pressure is almost same. Okay, after that you're supposed to select this. Here you can give the name pressure animation. Okay, and select OK. So basically we will be having one animation which will show us the pressure variation. Similarly, I want to add another. So I'll again go to solution animation, again new object, contour. Okay, I want only for interior and uh, interior fluid and plate. After that, which parameter? Now I want the animation for velocity. So we will select the velocity. Okay, after that save and display. Okay, after that OK. We forgot to select the contour. Okay, select the contour and then OK. Okay, if you want you can rename it. We will say velocity animation. Okay, so click on the OK. So now our solution will going to find the solution, and it will also going to show us the animation of these two quantity. Then we are going to run the calculation. Our model is set. Basically the next part is calculation part. For how many iterations, we will say we will see whether 250 iterations are okay or not. So we'll calculate. So during the calculation, what is happening on the animation, you can also able to visualize that. Okay, so this is the formation of our velocity profile. Okay, this is the formation of pressure profile or pressure variation, and these are the calculations which are being done. Okay, basically our solution will converge if this error, okay, all these calculation they are denoting the error. So when this value of error, it becomes equal to 1 into 10 power minus 6, which is set by the software. If you want to upgrade that, so you can go to calculation activities. Okay, and here in residual you can uh, convey that value, 10 to the power minus 12 or 10 to the power minus 18. Okay, but we will set the standard value, and we will see at what values our solution will become converge. So this is our velocity profile. Okay, so our solution is converged. Okay, so you can see our solution is converged only after 59 iterations. Okay, so we had properly modeled the problem, it means. Okay, then if you want to see the contour, so you can go to contour. Okay, in contour we had already set the first contour as pressure contour. Okay, we will close these windows first. Okay, so if you click on save and display, so it will show you the pressure contour. Okay, likewise for contour 2, it will show us velocity variation. Okay, so this is a velocity variation which is taking place. Okay, and if you want to see the animation, okay, so we will go to animation and solution animation playback. Okay, after that from here, okay, you can control the speed. Okay, this is the button for play and this is a button to stop. So I had set some speed. Okay, and basically we are going to see the pressure animation. So we will start the play. So you can see when the flow is taking place, how the pressure variation is taking place. Okay, it is showing us frame by frame. I think the speed is slow, so we can increase the speed. Okay, we will increase the speed for next animation. Okay, now this is the formation of a velocity profile. Okay, so you can see how velocity profile is being built. Okay, now here you can see near the plate surface, okay, the values are green. So green values indicate the velocities are low. As you are moving away from the uh, plate surface, the value of velocity is increasing. You can see from green it becomes yellow, then it enter into red zone. In the red zone the velocity is maximum. Okay, so likewise the velocity boundary is formed, okay, which already all the theory you had learned in fluid mechanics. Okay, now we are going to see the post processing part in CFD post. Okay, so now our calculations are done, so we will close the front. Okay, now you can see the calculations are done, so we will have a green tick on the solution. Now we will directly right click the results. So from result, basically we are going to open the CFD post. So we had to wait for a while for the window to get open. Okay, so CFD post window had been open, and this is our model. Okay, now if you want to add some line or some plane, okay, so you can do that from this location tab. Okay, after that if you want to see the vectors, velocity vector, how the velocity is flowing, uh, what is the direction of velocity vector, so you can plot that from this vector profile. Then for contour, what is the pressure contour, what is the velocity contour, we can plot from contour. Okay, also we can see the streamline, how to plot the streamline we are going to see. Also see, our case is a 2D case, so in this case volume rendering will not take place, but if it is a 3D case, so contour will show us the 2D variation, and volume rendering it will show us the 3D variation. Okay, and here there is a solution or animation. Now we will see how to use this animation also. So first of all we will go to contour. Okay, now in contour, uh, where you want the solution, I want it for fluid symmetry 1. Okay, you can select anything. Then what is the precision? So I want the scale precision to be 150. That means whatever the scale is there, that scale will be divided into 150 different sections. Okay, then uh, I want it for the variation of pressure. So you can select the pressure variation, pressure here variable, and then apply. Okay, so now you can see here. Okay, now you can see here the legend is a little bit of difficult to understand. So we will go to, first of all we will go to legend. Okay, this legend is nothing but this scale. Okay, this rainbow scale. Then if you want to change its orientation, you can change here. You want it at the center, you want it at the right or at the left. So from here you can see its location. It is located at the left side. Okay, if you want you can locate it at the center, okay, at the right, but we will kept it to left. Okay, after that in appearance, see, this is a scientific way of showing the values. Okay, if you want the fixed value, so you can select here fix and apply. So you can see here it is showing in the integer form. Okay, what is the value of pressure? Now this red region indicates here as the flow is obstructed by the plate, so here high pressure region is created. Okay, so here the value of pressure is more. Okay, after that here due to formation of boundary layer in this region, basically suddenly the velocity reduces, so sorry, increases, so the value of pressure is reducing. Okay, and after a particular length this pressure almost become constant. Okay, so this is the way in which the interpretation is done. Okay, after that, okay, Now there might be a question in your mind, what about the plate? If you want to see the plate pressure variation, okay, it is not showing because the fluid flow is not taking place. Okay, so you can apply for plate symmetry 1 or plate symmetry 2, it will not show anything because there is no change in pressure because the plate was stationary. Okay, after that we will see the velocity variation. So from here we will select the velocity and will apply. Okay, now you can see here, now this was the wall, so basically no slip condition exists on the wall. So you can see the blue line indicates zero velocity. Okay, so velocity is almost zero near the wall. Okay, then again in the plate, near the plate region, you can see here the blue region is there. Okay, and this blue line, it is extending over the entire plate surface. So basically the no slip condition is existing and the velocity is zero near the plate surface. Okay, now as you are moving perpendicular to the plate surface, okay, you can see from dark blue it is converting to light blue. So light blue indicates 0.1 to 0.2. Okay, again as you are moving away, so basically inlet velocity was 0.5 which we had defined, but you can see in this region the velocity become almost equals to 0.7. Okay, so this is taking place because the passage area, you can see this passage area, here the passage area is more and here the passage area is less. So in this region the velocity increases and you can see this yellow line. So this yellow line indicates the boundary layer. Okay, so and after that, see, for some region up to this region, basically there is a increase in the blue region. Okay, so basically it indicates laminar region, and after that the thickness of boundary layer, it is slowly reducing, and after that this thickness is constant. So in this region where thickness is constant, so this is turbulent boundary layer region. Okay, so this is a way of interpreting the contour. Okay, so I think you might have understand how to interpret the contour. Okay, after contour we will see the streamline. Okay, so we'll select this streamline. Okay, after that, which type of, see, 3D streamline is not because our geometry is a surface geometry. After that, on which surface I want it, on the fluid symmetry. Okay, you can select anything. We will say equally spaced. How many, okay, first of all we will see how many points. So we had applied the 25 points. 25 points means 25 streamlines are created from 25 inlet points. Okay, you can increase them to 100. Okay, you can increase them to 125, whatever you want. Okay, so these are our streamlines. Okay, after setting the streamlines, okay, go to animation. Okay, so that streamline will be appear, and from here you can control the speed. Okay, and you can see the animation, how the fluid particles are flowing. Okay, I think more speed is there, so we will make it slow. Okay, so you can see here how the fluid particles are flowing. Okay, so in this way you can create the animation. Okay, animation of fluid flow. So in this way we had completed our first problem. Okay, so we will exit this CFD post. Okay, so if you want you can save the project. Okay, I'm going to save it as I can give any name, boundary layer. Okay, boundary layer 1 2 3. Already I had one file with boundary layer name. So in this way you can save the all the files. Okay, so we had done our first problem. Now we will see our next problem. So for setting the next problem, again we'll go to file, new, and we'll select the new tab. So this tab will automatically close and new Ansys tab will appear. Okay, after that again we will go to fluid flow fluent. now I think in first problem we had already discussed in detail everything. So here we are not going to explain everything, okay, because I think already we had spent a lot of time in problem number 1, so we are supposed to complete this problem quickly. So in this problem we are going to see uh, the sudden contraction, okay, the problem of sudden contraction. So we will go to, again we will take the units in centimeter, we will say xy plane, sketch, again look at, so we are in xy plane now, then we will go to sketching, okay, in sketching we'll draw rectangle, later this is our rectangle number 1 and this is our rectangle number 2. So contraction of the fluid flow path is taking place. We will go to dimension, we'll define the width here, let this width be 25 centimeter and this length of the pipe is also 25 centimeter, okay. After that, distance of this, okay, we will say this as 5 centi, or let it be 10 centimeter, and this distance let it be 5 centimeter, okay. After that, the entire length here it will be 20, double of 10, okay, and we had here defined as 5, so we'll define this length as 10, okay. After that, you can see here this line we are supposed to delete, so we will go to modify. In modify we will select the trim and we will trim this lines, okay. So basically it had become a single geometry now. Again we will go to concept, surface from sketches, sketch 1, apply, and here we will generate, okay. So you can see simply our sudden contraction problem has been generated, modeling is done. So we will quickly exit or close our design modular, okay. Then we will go to mesh, edit mesh, again we have to wait for some time for the mesh modeler to get open. So it is getting open, we had to wait for 20-30 seconds. Okay, so problem, we can see the model which we had modeled there, okay, it is appearing here, okay. We know our mesh, if we directly go for a mesh, so that will be unstructured mesh. We'll go to sizing, okay, we will select this edges, edge 1, sorry, we had to first of all select the edge, then select the edges 1 2 3 4, okay, apply. So we had selected these 4 edges, we want to divide them in 100 divisions each, okay. Then again we will go to sizing, okay, let this it was 20 centimeter, so we will uh, divide it into 40 edges, okay. After that, sizing here, this edge, apply, I think 10 centimeters, so we will divide into 20 divisions, or let it be 40, it be 40 and it be 80, okay. After that, again uh, mesh, insert, sizing, and these 2 edges, okay, apply, then 10 centimeter, I think so, 20, okay. After that, we want to map these divisions, okay, on the face, so we will say face mapping. After that, where we want to map, we want to map here, okay. So once the conditions are applied, you can generate the mesh. Okay, so we had to wait for a while. Okay, so you can see our structured mesh has been created. Okay, after that the next step is applying the or defining the boundary conditions. So for that again we will select the edge. We want to go for sudden contraction, so this will be our inlet. If you want to go for sudden expansion, so this will be our inlet. Okay, so define this as inlet, define this edge, create name selection as outlet. Okay, after that this edge, this edge, this edge, this edge, this edge, and this edge. So total how many edges? 6 edges. Okay, after that right click, create name selection, and you can define that as wall pipe. Okay, that is a pipe surface. Okay, so quickly we will see this is our inlet, this is our outlet, and this one, 2, 3. I think we had left here. So again you can click here. Okay, 5 edges only. After that you can click here and press Ctrl and apply. Okay, so all the 6 edges have been appeared. So you can see now this is inlet, outlet, and all the 6 edges 1, 2, 3, 4, 5, 6. It represents our pipe wall. Okay, so our conditions are set. So we will quickly close the machine. Okay, after that our next step is update the mesh. Okay, so we had to wait till a green tick appear here. Okay, okay, so now you can see a green tick appear here, and so we are ready to go in Fluent. So we will double click, we will click on the double precision and we will say OK. Okay, so in this way a Fluent window it will open. We have to wait for 20-30 seconds. Okay, so our mesh has been uploaded here. So you can see here again our first step is whether we want to go for study or transient. So we will go for study. It is a 2D problem and it is a planar surface. Okay, then here again there is no multi-phases involved. There is no energy transfer, heat transfer is taking place. So we'll directly go to viscous model. In viscous model, basically we will select K epsilon. Okay, and we will take the standard values. Okay, after that all the other model are not applicable to our problem, so we will not apply them. Again material. Okay, now see in this problem we want the flow of water through the pipe, so we will go to materials. Okay, in the material we will upload the fluid, so we will go to fluid database. Okay, in the fluid database we want which fluid? Water liquid, not water vapors. So we'll select this water liquid and copy. Okay, so you can see here the water liquid appears. Okay, likewise if you want to specify the pipe surface, pipe material, okay, so you can specify recall from library, but we will keep it for aluminum for our problem. Okay, then we'll go to cell zone condition. So in cell zone condition, whatever the surface body, that means this green surface, it is a solid or fluid, so it is a fluid. Which fluid? By default it will take air, but we are supposed to change that. Okay, you can see here by default it is air, we are supposed to change it to water liquid. Okay, after that we are supposed to set the boundary conditions. So basically in our case only inlet and outlet. Okay, so we will specify the inlet velocity. Okay, let it be 0.5 meter per second because it is a considerable good velocity. Okay, outlet is pressure outlet and this is a pipe wall. Okay, after that we will initialize the solution. Okay, we'll go for standard initialization and initialize it from inlet. Okay, after initialization we will set up the pressure and velocity animation. Okay, so same process, we will go to contour. In contour we will we want it for, let it be all this surface. Okay, and save and display. Okay, so right now no fluid is flowing, so pressure is constant. Okay, after that select this, you can name it pressure. Okay, and okay. So one animation is set. Again set the second animation for velocity, so VE velocity. Again we will go to contour. In contour we will select the velocity and velocity magnitude. Okay, save and display. So you can see, oh, no flow is taking place, so velocity is constant. Okay, after that select this contour 2 and okay. Okay, so we had set these two animations. Okay, after that we'll go to run calculation. Now let it be 250 for instance. Okay, I think our solution will be converged. And you can see here our solution is being done. So this is a velocity contour which is being formed. Okay, this is a pressure contour. You can see there is a drop in pressure and there is an increase in velocity because of reduction in cross section area. Okay, and here you can see what are the values of solution. Basically your solution will not converge because the error are not that much big, but the error are constant. You can see it is a flat line. So if it is a decreasing line, so we might have reached to convergence. Okay, after this 250 calculation we will get the exact solution. Okay, or for more precision you can go for further calculation, but it will increase the time. So I am stopping pausing the video till the calculation complete in order to save our time. Okay, so you can see the solution is converged after 118 iterations. Okay, so we had reached to a converged solution. Okay, so quickly we will see our animation. We'll go to solution, playback animation. Okay, so first of all we will see our pressure video. Okay, so you can see how the in the red region the pressure is high, it is decreasing, and you can see there is a reduction in cross section area due to jet formation. So here the fluid is standstill, so pressure is 0, which is indicated by blue line. Okay, so this is a vena contracta, minimum cross section area. After that we can again see the velocity animation. Okay, you can see the velocity is increasing. Okay, again in this region the velocity is the fluid is at rest. Okay, cross currents are formed, so here blue region is there. Okay, so velocity is 0 in this region. Okay, so we had seen the animation video, so we'll quickly close the fluid. We'll go to CFD post. Okay, so you can see the calculations are done. So solution is green tick. We'll open the CFD post. Okay, so our CFD post is, I think, open now. Okay, so again we will see contour. Okay, at what which region we want contour? We want contour of this green region. Okay, you can here 120. Okay, and apply. So you can see here pressure variation. Okay, the pressure is reducing, and in this region some fluid, it is having some whirling motion, so that fluid is not flowing, so pressure is 0. After that the pressure is increasing. Okay, you can see the scale. Okay, again for velocity you can go to velocity and you can see the velocity variation. Okay, the velocity is constant here, near the pipe surface, pipe wall, no slip condition exists, so blue line is there, velocity is 0. Again in this region basically some fluid is revolving. Okay, so almost it is at rest. Okay, so you can see, and in this region the velocity is high. Okay, so this is our velocity profile. Okay, after that the streamline. For streamline we will go to streamlines. Okay, after that start from inlet. Okay, and it is not a 3D streamline, it is a surface streamline. And how many streamlines you want? Let it be 100. Okay, then okay, we have supposed to untick this contour and then apply. Okay, sorry. Okay, so we had to select this 3D streamline and then apply. Okay, so you can see here, this is our streamlines. Then for viewing the animation, you can click here, you can select this streamline. Okay, you can control the speed. I am slowing it. Okay, so you can see how the fluid particles are moving slowly. Suddenly when it reaches here, their velocity increases. Okay, and then again their velocity decreases. Okay, and in this region you can see this one blue point. Here the velocity fluid is at rest, so it was not moving, this blue point. Okay, again if you want to increase the accuracy, you can make it to 150. Okay, or let it be 250. You'll get more accuracy. Okay, but okay, also you can see here the fluid particles which are whirling. Okay, so they are whirling here. After that you can see this. Okay, the speed is very fast. Okay, so you can see this fluid particles of water particles are moving, and the remaining fluid particles within a fraction of a second they had. Okay, so in this way, okay, we have to stop this animation first and then close. Okay, now we will see what is the how to see the plot of velocity variation along the length. Okay, so for that we are going to insert one line. Okay, so we'll insert one line. Now for inserting the line, we know line can be plotted from 2 points. We are supposed to specify first point and second point. Okay, no need to specify the z direction because our flow is a 2D flow. Okay, so our point 1. So point 1 will have, I think the length was 0. Length was 25 centimeter. 25 centimeters. So let it be 0.25. Okay, it is in minus, so minus 0.25, and it will be plus 0.25. Apply. Okay, so we can remove this. So you can see, okay, from minus, see this is our x-axis. So here we are having origin. So our first point was minus 0.25, means 25 centimeter on negative x-axis to and 0 coordinate along y, and here 25 centimeter along x-axis and 0 centimeter along y-axis. So this is our line. Now we will go to chart. Okay, we will apply this chart. In this chart we will go to data series. Okay, and at what location we want along line 1. Apply. Okay, then you can go to x-axis. Along the x-axis we will keep the chart count, and you can put the value of chart count. Okay, okay, we are supposed to go at line, and here samples, we had taken the 10 samples, we can divide it to 50, so there will be total 50 points along that line. Okay, then we will go to our chart again. Where is the chart? Okay, this is our chart. Okay, so we had selected the line. Now what we want along x-axis, chart count, which is 50. What we want along y-axis, so we had selected the pressure, so it is showing the pressure variation. Okay, so pressure was high at the inlet, then this pressure suddenly dropped. This is the region of vena contracta where the pressure is minimum, and then the pressure increases. Similarly, you can see the plot of velocity. Okay, so you can see the velocity was less in this region at the inlet, then it was increasing at the vena contracta, it is maximum, and then again sudden expansion take place because of the jet, and because of that the velocity is again reducing. Okay, so in this way you can plot the chart also. Okay, so in this way we are going to complete our second session. In today's session we have taken the two problems, okay, and we have seen the complete solution of these two problems. In tomorrow's session we are going to see the analysis of 3D problem. Thank you very much for being a patient listener.